Mike. Thank you. Okay, let's move on to the next speaker, which is Professor David Rosen. David Rosen, I think, David, you should be reversed at the moment. Let me just do a quick check. David, are you reversed at the moment? Just do a quick check. That. Yeah, David, thank you. David's here. Let me try and introduce David. So it's good to see a familiar face again. David, it's good to see you. Let me try and introduce you to the audience. So David Rosen is a professor in the School of Mechanical Engineering at the Georgia Institute of Technology, or Georgia Tech. He's the director for the Rapid Prototyping and Manufacturing Institute at Georgia Tech. Additionally, he's the research director of the Digital Manufacturing and Design Center at the Singapore University of Technology and Design, or SUTD. He received his PhD at the University of Massachusetts in mechanical engineering. His research interests include computer-aided design, additive manufacturing, and design methodology, with a specific interest in the intersection of those topics on design for additive manufacturing. He has industry experience working as software engineer in computer vision, car, visiting research scientists at Ford Research Laboratories. There is a fellow of the SME and has served on the SME Computers and Information in Engineering Division Executive Committee. He is a recipient of the 2013 Solid Freeform Fabrication Symposium, or SFFS, International Freeform and Additive Manufacturing Excellence FAME Award, and is also the co-author of a leading textbook on additive manufacturing. Thanks, David. Thank you so much for taking your time to present, especially in the time difference back in Georgia. I can see your screen, so let's get started, David. Thank you.
All right, well, thank you for that introduction. Thanks for the invitation to speak here. Hopefully I'll say something interesting here. So I'll talk about my perspectives on additive manufacturing and design for additive manufacturing. And here's the outline, such as it is. Of course, the center of this, right, is design for additive, but really design for additive becomes important, relevant, and really interesting when you tie that to additive manufacturing or product development. So what I'm going to try to do is touch on these linkages between design for additive and the various boxes that I have arrayed around here. So we're going to look at various contexts in which you can learn about design for additive. Let me start with kind of the big picture here. So in the United States, I'd say that manufacturing has received much more attention in the last 10 years. And that attention's come from the federal government down to local governments, down to individuals. In response to a lot of, in the last 10 years, the U.S. has created a network of manufacturing institutes. There are now 16 of them. And the first one was really focused on additive manufacturing, and it was founded in 2012. So since then, we've added 15 more. I mentioned this to kind of highlight the overall interest in the U.S. on manufacturing and additive manufacturing, but more specifically because each of these manufacturing institutes has their own workforce and education development program. And so America Makes has spent a lot of time and effort partnering with everyone from the National Science Foundation to the Society for Manufacturing Engineers and others to really come up with a comprehensive workforce and education roadmap that's relevant, of course, to additive manufacturing. So it talks about everything from kind of high school educated technicians all the way through PhD level research, industry practice, and a variety of different kinds there. Back in 2014, the U.S. National Science Foundation, along with America Makes, held an AM training workshop. And one of the results of that is just this diagram here, this sort of Bloom's taxonomy-like triangle that illustrates, again, different communities of people that could want to learn about additive manufacturing. And ways of delivering education about additive and different kinds of activities and the skills and knowledge bases that will result from all that. Then, of course, there are lots of written resources on additive manufacturing and design for additive. I, of course, am shamelessly promoting my own textbook in this area, but I'm just using this as an indication that there are, you know, a whole raft of textbooks, other books, popular literature, as well as lots and lots of websites with good information about additive and design for additive. So let me start going a little bit further now and looking at design for additive in the context of industry and product development. And I'll highlight a few different more sort of industry or practice-oriented programs that have been created. So one of the standards institutes, the ASTM International, has an additive manufacturing certification program. There are 8 parts of this. Society of Manufacturing Engineers, or SME, along with UL, has a separate certificate program, although there's a lot of linkages and overlap between them. Penn State University has a master's program. They started a couple of years before Nottingham's master's program in this area. And of course, you know, most engineering programs in the U.S. have some kind of undergraduate manufacturing or additive manufacturing course where additive content is offered. And then, of course, a lot of different companies have their specific training. I'll highlight the ASTM certification course for a minute here. There are 8 elements of that course. One of them is on design and simulation. Each of these 8 elements is taught in a 4-hour kind of module, and you can, I mean, all 8 are required for certification, but you can then emphasize a particular role, whether it's an operator, quality engineer, etc. And then the other thing I'd like to highlight here is that our host Yujin Pei and I offer the design and simulation module for this certificate course. SME and UL, they also have a certification course. They offer certification at 2 levels, one just fundamentals and the second at the technician level. And there's a set of SME provided courses. You can see 5 beginning courses, 3 intermediate courses, and then of course one of these courses is on design for additive. America Makes has involvement in this one in particular. But of course, they are involved with ASTM International in a variety of different ways, and of course ASTM, I should say, has a lot of linkages to ISO as well. I mentioned the Penn State University master's program. There are actually 3 programs that they offer, although they're related. So for resident students, they can get a Master of Science degree that could include a thesis or not. For online students, typically these are full-time employed engineers who in part-time are taking courses online. A lot of the U.S. universities have that kind of a program. Anyways, they offer a master's in engineering for these online students. You can see on the right the image there, emphasis on science, process, materials, and then also design. Hands-on lab in the middle, because with manufacturing and additive, you learn the processes best by doing some additive manufacturing. You learn design for additive by doing design and getting some hands-on experiences. So this program has been very successful. It's attracted a lot of industry interest. So now let's take a look more at the research element here. If we look at like PhD level research happening at universities, this is a snapshot of the course that I teach at Georgia Tech. It's a combination of a focus on the fundamental sciences underlying additive manufacturing, looking at in this case if you want to grow a thin rib in stereolithography, and you do high fidelity simulation of the stereolithography process, what is the resultant part going to look like? So that that's indicative of a lot of the content in the first month and a half. We transition into more selection and then design for additive for the next month or so. There's a big couple-month project that the students do, and most of the student projects will be to design something that will take advantage of the unique capabilities of additive manufacturing. So, and of course, in this course, we also have lab exercises. So Students will go in the lab, they'll build several parts, they'll measure them, they'll try to characterize them, and then understand the causes of form or dimensional problems that arise, and relate those problems back to the underlying physics of the process. I mentioned the project where students design a device. This, I'll just give you one snapshot of a quadcopter design that the students thought about, designing for kind of material extrusion to make the body, but then also using direct write for the electronic circuits embedded in the structure. And because they're PhD level graduate students, they know finite element analysis, they know CAD, and so they used all of that in their projects. So I also offer the course to both on-campus as well as online master's students. And the online students, again, typically they're working engineers, and so I know that spun off out of my course periodically are several industry programs that the students then took their project ideas and extended it into the company. The point is that there's a lot of really interesting things that we can do at the more advanced research level in terms of design for additive education, and linkages to other aspects that we've been talking about here. A few ideas about the linkage between design for additive and business. Professor Hod Lipson, who used to be at Cornell, now is at Columbia University. When he was at Cornell, he introduced this design for additive course, and the one thing that really strikes me about what he did, I thought it was very clever. He had the students develop a design idea, but then come up with a business model for that product that they had developed, and then post that product and business model on Kickstarter to see if there'd be interest in the broader community funding the development of that product. This is as part of a semester-long course. This is really a creative way of doing it. I'm not sure I would have done very well on that. I'm not much of a marketing person, but very interesting sort of model to offer education. Now, more broadly, most universities now have some kind of entrepreneurship programs for students. At Georgia Tech, we have what we call the CreateX program. It's been going on for about 10 years. It's very popular among our undergraduate students. There's been more than 5,000 students involved across 38 different majors. 230 startups or so. Most don't go all that far, but some have been very successful, including several tens of millions of dollars worth of revenue from a couple of the different startups. I mentioned this for a couple of reasons. It's an entrepreneurship program, so it's far beyond additive and designed for additive. However, the program for the undergrad students really involves a 3-course sequence. The second course in that sequence is a semester-long course called Idea to Prototype, where the students develop a working, physical prototype of the product, along with faculty assistants. And so while they're developing their product idea, they have to design it, of course. They have to think about manufacturing. They have to think about manufacturing a prototype, but they also have to think about scaling that up to production manufacturing. So, there's a lot of good technical, design and engineering that has to go on, as well as manufacturing. And in support of this course in particular, at Georgia Tech, we have a network of maker spaces. I'll talk about that in a minute. And so the students, of course, become aware and then get some introduction to these maker spaces so they can actually, execute their physical devices. So that leads us into informal exploration, or the informal education environments, the maker spaces. At Georgia Tech, like I said, we have several of these kind of maker spaces. The first one and the largest is the Invention Studio out of mechanical engineering. There's a lot that I could talk about that. I'll just say that, we have about 3,000 square feet. We have an army of undergraduate students who manage this thing. There's tools available, everything from very simple hand tools to high-end 3D printers, CNC 5-axis CNC router, things like that. And our Invention Studio is on the second floor of the main mechanical engineering building, and that entire second floor really is devoted to makerspace, hands-on activities, manufacturing, and things like that. So next to the Invention Studio is our machine shop, which we call the Montgomery Machining Mall. And then adjacent to that, we have our ME2110 course that's a sophomore level design, build, compete course. And of course, like I said, we have additional maker spaces. So here's a snapshot looking at the outside door of the main Invention Studio room, second floor of the main building here. There's an atrium area out in front. Overall schematic, right, we're in the atrium right about here. I don't know if you can see that. And then in the main Invention Studio, we have the hub, the metal shop behind that, wood shop. I mentioned the machining mall on the upper right, big atrium. The thing to note that I mentioned the atrium because we have a bunch of tables out there, and so a lot of student group work is done for their design courses in this area. They'll make the parts in one of the labs, and then collect parts in the atrium area, assemble things, test things, et cetera, et cetera. And then in the lower right, I illustrate the ME2110 lab. So everything is all integrated in one space. Here's a snapshot inside the Invention Studio. You can see individual and group workspaces, a bank of 3D printers. There's other 3D printers available in the space. Behind the photographer here is a bank of 5 laser cutters and then some other facilities. We have an electronics area in one of the corners of that Invention Studio. The metal shop behind the 3D kind of makerspace area is the metal shop. A lot of hand tools, but then also some higher end kind of tools. We have a wood shop with like I said, a 5-axis CNC router that's about 2 meters long. The bed is about 2 meters long, etc. Adjacent to all this is our main machine shop. We call that the machining mall here. We have 6 full-time people that work in there, mainly supporting the research enterprise. But a lot of the work here, it supports research, but we have PhD students and master's students, graduate students doing the research. And there's also some opportunities for undergraduate students to get trained on various machines here. Again, it would be part of a research program. So I've talked about more informal education, makerspaces, things like that, but we use these makerspaces to also support the engineering curriculum, both in mechanical as well as more broadly in all the other engineering disciplines. At the freshman level, we have a course on engineering graphics, which is sketching, CAD, basic design. Students use SolidWorks here. And then we've added about a one-week module on additive and design for additive. So as part of their project work, as part of their design work and CAD work, students pick one of their parts to actually get printed on one of our putter bed fusion or selective laser sintering printers. This isn't, well, so we have full-time staff who actually operate the printers because it's more of a high-end machine. You can't have 500 undergrad students all clamoring during the semester to use this machine. But this accomplishes a number of objectives here. First of all, it gives them some feedback about these kind of automated digital manufacturing tools and how well they work, what kind of tolerances can be held. But it also introduces the students to manufacturing, to the Invention Studio and the facilities on campus to make parts and do manufacturing. So if students have an interest, they can always pursue their own project or other course projects using the facilities of the makerspaces. So this is just one example snapshot of some of the student work in this freshman level course. Again, they'll pick 1 or 2 of these parts and get them printed out. Nothing prevents them, though, from going on to one of the low-end 3D printers and one of the FDM printers and fabricating the parts as well. At the next level, the sophomore level, we have our ME2110 course, which is a really comprehensive, intro to design theory and methodology kind of course. But more importantly, it's a design, build, compete kind of course where in about a month and a half, the students design, build, and compete an autonomous robot. There's a corresponding lab with this course that teaches the students everything from how to use a bandsaw to program a microcontroller, a little bit of pneumatics, so they have actuators for their robots, things like that. And then we have a competition that is focused on here's one of the competition spaces, right? We have 4 different project groups with their machines that are all trying to compete and compete with each other and compete to get as many points as possible. Sorry about my dog barking here. Anyways, it's a lot of fun. Students learn a lot. They also learn a lot about the detailed design and how to make things work in the real world with real forces and gravity and all that kind of stuff. And of course, they have the access to the Invention Studio and their own lab facilities. They get a lot of hands-on design for manufacturing, design for additive experience in this kind of a course. And at the end of the semester, we have a big competition. This is sort of like the Roman Colosseum with the spectators hanging down, and it's a lot of fun. Maybe after COVID, you guys can come over and visit. And anyways. Let me just conclude by saying that, again, in the U.S., there's been a huge emphasis on advanced manufacturing and additive in the past years, a lot of investments, and we need curricula to support all that. I'm one who really thinks that education works best in a more authentic environment, and so I look for these kind of opportunities to integrate design for additive and additive with other aspects that can engage students and get them excited about the topic. So that's why I present all this in the context of these other kind of ideas. So I've talked about some approaches to design for additive education. There are master's programs in additive. There are individual courses on additive. And of course, there are design and manufacturing courses that include a lot of additive content. On the industry side, there are certification programs for professionals offered by several of the nonprofit organizations and things like that. But across the country, and I think a lot of the world, there's been this growth of the informal education and exploration opportunities with makerspaces on campus, but also makerspaces at local libraries and other sort of community facilities. So it's really interesting kind of time to be in this area, looking at the growth of additive, the proliferation of low-cost 3D printers and what people are doing with them, as well as all the way to PhD level kind of research and education. It was really interesting listening to Chris talk about the CDT at Nottingham, and the success that they've had there, and what they've how they've integrated that CDT with their larger set of activities. So with that, I'll conclude my talk. Hope you found this useful and interesting, and I'd be happy to answer any questions.
Thank you, David. Really appreciate that. Let me have a look at the chat box. I think again, there's some very interesting questions coming through, David. So thank you very much once again. There's a question from Masher. He says, "Thanks, David, for such a great talk. Did Hard Lips and students have any success with the Kickstarter ideas?" It's a good question. And also, do you have any tips for those of us who wish to set up a university makerspace?
Yeah. So first, the Hod Lipson course. Unfortunately, that was maybe 5 years ago. I think it's I think a conversation that we had at a conference or something like that. I don't know much. I don't know many details, but I think that Hod, at least his impression was that was a very successful course. That it's one thing to come up with a paper design and maybe print it, but it's another one to put it on Kickstarter and solicit interest from a broader community. You know, people will vote with their feet and their money. So I don't, but yeah, unfortunately, I don't really know any more specifics there. In terms of advice about maker spaces, yeah, number one, engage students. You've got to have the students involved. It's really helpful if there's a group already on campus, a group of students already on campus who's interested and you know, who want to be engaged in the development of such a space. Certainly, you know, our Invention Studio went from, you know, a few tools in a room that we, you know, commandeered from someone else to now we've taken over the whole second floor of the you know, of the building. So yeah, you've got to start somewhere, but it really depends upon, you know, having a set of committed students who want to help build this thing. At least a couple faculty who are interested in supporting them, and then of course you need administrative support because you need space. It's helpful if there's some activity on campus that allows you to kind of have proposals to buy equipment, things like that. So yeah, there's, I mean, we could have a very long conversation about how to get these things going and started. But really, you know, we started with a couple of faculty who were very passionate, but also a set of, you know, 10 to 20 students who were already engaged, who really wanted to build this program and were willing to take ownership and leadership. Because you need the students to mostly manage that space. Hopefully that, I mean, again, I could go on for a long time, but hopefully that provides some direction.
Thank you, David. Thank you very much. I think we've got a couple more questions, but I see a virtual hand being raised up by Montgomery. Montgomery, would you like to ask David a question? No, maybe we'll get back to Montgomery again. Okay, I can see another question from Joey Bjorn, Elisa. So he says, okay. Montgomery, please go ahead.
Hello.
Hello.
Am I audible?
Yes.
Am I audible?
Yes, you are.
We can hear you.
Oh, okay. Thank you very much for offering me this opportunity. Mine is just it cuts across the presentations that I have so far had on this discussion. When I heard about this design for additive manufacturing education, in my mind, I was thinking that maybe I'll hear most of the discussions based on the grassroots development. That is to say, the introduction of this additive manufacturing education at lower levels of education, like maybe your formative years of schooling, like your primary, secondary schools there. Mm-hmm. And I think that way it will be more easy to disseminate the appropriate knowledge there. Mm-hmm. Now what I see is like mostly the discussions are focused at advanced level. That is your masters, your PhDs, and all that. So I want to know if maybe you consider grassroots development with respect to maybe being participative in say curriculum development and so on and so forth. And also, how do you mobilize the community? Like maybe if you look like here in Africa, I'm in Botswana. In Africa, you find that take for example, when information technology came on, there was this we used to form groups in communities to teach them basic applications of computers and so on and so forth. Are you not considering doing that as well? Thank you.
Sure. Given that I'm a university professor, I'm going to talk about what I know and what I do. But certainly there's a huge interest in technology at the K through 12 level. And in fact, again, in the last 10 years with the proliferation of low-cost computers, low-cost computer-aided design software, and low-cost 3D printers, there are many, many schools, elementary schools, middle schools, high schools that have small maker spaces, that have opportunities for students to learn about computer-aided design, learn about 3D printing, and more just incorporate these kind of IT technologies in science and in other kind of education programs, and again, from first grade all the way through high school. It's because in the U.S. I think Europe, there has been a lot of penetration of this kind of technology in K through 12. I mean, it's hard to provide much more specifics on this other than to say that, yeah, I mean, there are thousands and thousands of schools that have CAD and 3D printers in them. Students get access to them. Students can do everything from art and art on the computer printed out to some engineering and science support. And in middle and in high school, back when I was in school, we had machine shop and wood shops, things like that. Well, now those have become CNC and 3D printing kind of courses that students can take. So there's again a huge interest in pushing this kind of technology down into K through 12. We have quite a few programs in the U.S. That are focused on this train the trainer or teach the teacher kind of model, where workshops or courses will be held for school teachers to get them up to speed, and then they can go and develop their specific courseware and course modules for their students in their classes. Okay, so yeah, it's a huge area, but I think I'll stop there. Okay.
I think you mentioned really good points in terms of what we call widening participation, as well as what we call inclusive teaching. So these are really key enablers, I think, in my opinion, would be the future of providing a bigger uptake of additive manufacturing education. Thank you, David. I'm quite mindful of time, so I've got one more question, again, I think from Joey Byrne, if you don't mind, David. So he's asked you about a question regarding printed electronics. He says, how do you see the current and future status of 3D printed electronics, or maybe just printed electronics, PCBs and sensors?
Well, yeah, this is a topic of tremendous interest in industry and research. There's already and have been good quality printers for printed electronics for the last 15 years really. So yeah, developing process developed materials, developing more complex and sophisticated electronic circuits. There's huge interest in that topic. One of the challenges is power. With these kind of printed electronics, there's a limit on how much power you can put through them. Another area of research interest is, of course, active electronic components. Passive are easy enough. I can say that from a professor point of view. But active devices are quite challenging and will require new materials and processing methods. If you need a standard 2D printed circuit board, it's likely that current microelectronics and printed circuit board fabrication will be sufficient, at least in the near future. If you want to do other things, 3D packaging, where you have packages or electronics that have to conform to shapes or fit in small areas with special shapes. These are applications that I think will really where additive can have a big impact, because it's difficult to use standard printed circuit board, fabrication and population sort of technologies there. So, said a slightly different way, potentially complex niche applications will be the first real area that'll see a tremendous amount of advancement. It'll be a while before additive takes over from conventional microelectronics and printed circuit boards. And in fact, I don't think you can compare a $5 billion, electronics foundry with additive manufacturing. Intel, AMD, other chip manufacturers, they're gonna use the high-end microelectronics production for many years in the future, I think. But additive will have its applications in more macro scale kind of packaging kind of applications, I think. Huge topic, a very interesting topic.
Absolutely. I think when you have the convergence of two very big topics, electronics and additive manufacturing coming together, it just sets out totally a new field altogether. Thank you, David. Really appreciate your time for today. Right, thank you so much for the opportunity to present your work as well as what you guys do at Georgia Tech. It's very inspirational. Thank you. But we'll be in touch again, David. Thank you so much. If you've got any questions, just feel free to use the chat box, and I'm sure David will probably pick up on that. So thank you very much, David.
Okay, I think I have. I'm not sharing anymore. Right, take it away.
Yep. Thank you. Thanks, David. Right, take care and have a very good day ahead of you. Thank you. Thanks, David. Okay, I think we need to move on. I'm just quite conscious of time. So we have our next speaker,